All right, so this is number 7. It says use the modified form of Kepler's third law and Saturn's mass to calculate the period in hours. That's important, right? Calculate the period in hours for the material in the inner and the outer rings of Saturn. All right, we're going to round one place past the decimal. Just anyhow, the semi-major axes are. So this is the inner ring is 90,000 kilometers, and the outer ring is 136,000 kilometers. And it says, can you see why the rings cannot be a solid? They give us Saturn's mass as 5.68 times 10 to the 26 kilograms, right? And we're going to round to one place past the decimal. So just to let you know, all right, so how do we do this problem? So if you look on the formula sheet, there's number 7 that we're doing right now. I just copied it over there. And then if you come down here, let's see, went a little too far. If you come right here, okay, so this is the original, my mouse, this is the original modified version of Kepler's third law. This is so if you rearrange this equation and you solve for p, the p and the m switch places, but of course it's p squared. So if you take the square root of both sides, the p, which is the period, is the square root of 4 pi squared times the semi-major axis, that's what d is, cubed, divided by big G, which is always the same number, 6.67 times 10 to the minus 11th, but this time divided by the mass, and that'll give you the answer for the period in seconds. All right, so that's what we're going to use. All right, so we're going to use this form of it, which is going to be on your equation sheet. All right, just to let everybody know. All right, so here we go. All right, so the first thing that we have to do is change the distances here, the semi-major axis. So I'll start with A here. So for A, it's going to be D is equal to 90,000. So 90,000, and since it's kilometers, right? Kilometers, but we know that there are 1,000 or 10 to the third meters in 1 kilometer, right? So the kilometers cancel. And so when you multiply 1,000 times 90,000, you get, of course, 90 million, right? So this would be 90, and then 1, 2, 3, 1, 2, 3. All right, and that's, of course, in meters. And now you could rewrite that as, 9 times 10 to the 7th, right? 9 times 10 to the 7th meters, right? And the same token goes for part B. The distance for the outer ring is 130. What is it? 136,000 that's a 0 kilometers. And same token is 1,000 meters in 1 kilometer. Kilometers cancel, and so this becomes all right. So you could write it out 136,000,000 meters, or you could move the decimal place 1, 2, 3, 1, 2, 6, and then 2 more, right? So that becomes 1.36 times 10 to the 8th, right? Yeah, I mean, you can literally just count the decimal places, right? So again, where's my mouse? There's 3 of them. There's 6 of them. 7, 8. All right, so 1.63 times 10 to the 8th. Of course, that's also meters, and we need that for this, right? So here we go. So the period is equal to the square root of, right, and remember the period's going to come out in seconds, right? 4 pi squared times, so we're going to multiply by each of these distances. I'll go start with the first one. So it's going to be 9 times 10 to the 7th, but we've got to cube that, and then we divide by big G, which is 6.67 times 10 to the minus 11th times the mass of Saturn. Let me make this a little bigger, which they give us as 5.68 times 10 to the 26th. All right, there we go. All right, so that's all. Those are all the numbers, and let's see if we can do this first one. All right, so here we go. All right. All right, so it's the square root. All right, and so it's the square root of. So it's you just gotta be careful with this. Okay, so 4 times pi, which is squared. 4 times pi squared. Times 9 times 10 to the 8th, right? Sorry, 9 times 10 to the 7th. 9 exp to the 7th. But remember, we got to raise that to the, so we raise that to the third power, right? And then we divide that by, and I'm going to use parentheses here because I'm going to divide it by two things that have to be multiplied together. All right, so divided by parentheses 6.67 times 10 to the minus 11th. And then we got to times that times the mass of Saturn times 5.68 times 10 to the 26th. All right, and I'll close parentheses, although you don't really need to do that. Close parentheses. All right, so that's, and then we're going to hit equals, and so that'll give us the period. All right, and in the period in, that did not work. I can already see that did not work. Huh. Okay, hold on. So, because when we're supposed to be able to divide it by 60 squared, and that should give us, yeah, that is not right. Okay, I'm not sure why this is not coming out right. Hold on, let me do it on my other calculator, and we'll see if we get the right number. All right, hold on just a second. All right, so just take me a moment here to do this. All right, so it's going to be the square root. I'm using a TI 83 right now. 4 times pi squared times 9 times 10 to the 7th raised to the 3rd divided by parentheses 6.67 times 10 to the minus 11th times 5.68 times 10 to the 26th. All right, so I'm going to do this in my calculator right now. I get, that's much more reasonable, 27,000. All right, here. So this is what I get in my TI 80. All right, so it's 27,468. All right, I just left it unrounded here. So then you divide this number by, remember, if that's the answer in seconds, you divide it by, there's 60 seconds, there's 60 minutes, 60 seconds in a minute, and then 60 minutes in an hour. So you divide it by 60, and then divide it by 60 again. So in other words, you divide it by 60 squared, and this will give us the number of hours for the inner ring to rotate around, once. All right, so it takes 7.7 hours. All right, so that's the answer for part A is 7.7. All right, so this is for part A. Part A. This is 7.7 hours. All right, and then for part B, I'll do part B on my calculator, just like I just did. It's just easier to use this calculator. The one on the computer is not the best, to say the least. So 4 pi squared times, all right, so it was 1.36, is that right? 1.36 times 10 to the, what would it be? Times 10 to the 5th, and then 3 more zeros would be times 10 to the 8th. All right, and then raised to the 3rd, and then divided by parentheses 6.67 times 10 to the minus 11th times the mass of Saturn, which is 5.68 times 10 to the 26th. All right, so the answer that I get when I do it is, here, let me just show you here. Kind of running out of time here, but I want to do this one. All right, so this is, it turns out in my calculator, it says 51197.78192. 192. That many seconds, all right? So 51,000, a little more than 51,000 seconds. All right, so if I again divide by 60 squared, that'll change it into hours. Divided by 60 squared. So this should be, I think it's about 14 hours, something like that. All right, so 14.2 hours. That's the correct answer. All right, so the outer ring of Saturn, the one that's furthest from Saturn, it takes 14.2 hours. Right, almost, going from the inner ring to the outer ring, almost twice as much time, right? And so if you ask yourself, why can't it be a solid? Well, if it was a solid, the whole thing would rotate with the same rate, right? It would take the same amount of time to go around once. Just like for the Earth. The Earth is solid. It takes 24 hours to rotate around once. So Saturn's rings cannot be solid. In fact, they're not. They are icy material. This icy, very shiny material, by the way. That's why we can actually see the rings of Saturn from the Earth. With even just a small pair of binoculars, you can actually see it. It doesn't take great amplification to actually be able to see this. All right, so that is number 7. I will continue with more of these in the next. Well, I don't know if I'm going to do that. Yeah, I'll do some more videos. All right, let's stop this. Oh.